Hello, I'm Tiffanie Leung. I am a media candidate in architecture, and my project is essentially, I'll just read it out for you. It's threading, sewing, handcraft with recycled textiles and construction practice, upcycling post-consumer clothing waste with do-it-yourself earth bag fabrication processes. What on earth is that? So I'll hopefully, be able to kind of explain this as I go along in my presentation today. Um, so to frame my research as a whole, I wanted to, take a look at, fast fashion waste that some of us may be familiar with. In 2020, the fashion industry produced the second highest amount of pollution, which accounted for 10% of carbon emissions and 20% of global wastewater. I mean, you sort of take into consideration that a single cotton shirt takes about 3,000 liters of water to produce in terms of like growing the plants and harvesting and dyeing it. It's quite a shocking and sort of urgent sort of alarm into how much we're depleting our natural resources. Within the entire the global context of textile production and waste, I can see that. So the red indicates countries that sort of send their textile waste outside of their borders. The blues are the countries that receive it, and the dark blues and blacks are essentially countries that received a lot of the waste. So you can see that in terms of like the global sort of economy and transmission, migration of clothing, the dark blue countries, which have the burden of producing these clothing and using their natural resources, they're also having the burden of taking a lot of waste that they cannot do it. To flip or to look at from a different lens of global scale, we can see that earth construction, not earth bag, but earth construction in general is very prevalent around the world. The most prevalently mud brick and adobe. And the reason why I bring this up is because my particular research, which is essentially focusing on this thing called earth-back construction, I think that there is an opportunity to sort of connect the two together. Earth-back construction is a modular rammed earth in situ construction technique that uses bag forms to hold earth as you're building it up on the wall. And so they can either be these long tubes that you can kind of imagine it as sort of manual 3D printing. Instead of using a robot, you're using your hands to like dig up and just like stamp everything down. And they can either be, earth bags can be in tubes or they can be in sandbags. And the reason why I sort of bring this connection is, if we consider earth bag construction as a sort of repeatable methodology, it can be applied in different contexts globally and also even within the United States. You can see earth bags present in places such as like California, even drier climates in New Mexico, and even some instances in more cold and so frosty places such as Minnesota. But all earth-back construction is essentially buildings using earth-back construction sort of use these sandbags to construct these domes or one-story dome styles throughout the world, wherever earth is available, which is everywhere, pretty much. And so thinking about the sort of material surplus of so-called waste or textiles around the world, and also taking into consideration that earthworks architecture is available, can be available all over the world. I think that there's an opportunity to bridge the two in order to reclaim quote unquote waste or textile waste as building material. If we kind of consider the quantifiable impacts of this and the broader implications of upcycling textile waste and earth-back construction, in 2018, the U.S. landfill, just the U.S. landfill, 66.4% of its textile waste, which is almost 11 tons. According to EPA, 68 pounds of clothing textile waste are discarded per person per year, which is kind of crazy to think about. One person can potentially discard so much. But we think about, of the donated clothing that people send to clothing banks and thrift stores, only 20% of that essentially makes it into and makes it back into the circularity stream. Only 20% of that is reused or resold. And the remaining 80%, which is about 800,000 tons per year, I think that can be recovered for earth reclamation. Which is like with the material. I mean, having surplus of material is great if you want to use it for something. So my main research question, which I will break down into smaller ones, is to what extent can post-consumer textile waste serve as an alternative for traditional polypropylene earth bags in terms of cost, structural performance, and constructability in small-scale earth bag walls. So essentially, I'm interested in knowing if I can use post-consumer textiles that can be reused. If I can use that for earth bag construction and kind of incorporate that as like a building material. And so the smaller secondary question that I have in order to answer that question, I get to think about, how do different bag dimensions and geometries made from reclaimed textile waste affect handling and structural performance during earth bag construction. So that kind of brings up questions about, okay, so what's the optimal size, what shape, compared to the conventional size, and can this be actually achievable with, garments, right? And so we look at the standard earth bag sizes and the sort of literature review. There's essentially 3 sizes. You have the 25-pound bag, the 50-pound bag, and 100-pound bag. And so conventional earth bags, literature says that, the 50-pound bag, which is pretty much, aligned with like the 50-pound weight requirement by OSHA, is sort of just right in terms of like the size and weight. 100-pound bags is way too big. It's probably the size of me. And 25-pound bag, they say it's too small, but I kind of want to argue that, if you look at the 25-pound bag, so the black is essentially when the bag is filled with earth. So kind of the footprint kind of shrinks a bit. That's sort of comparable to the larger end size of like an adobe brick. So I think that there's like opportunity to kind of reconsider, first of all, different earth bag sizes for different purposes in the wall. And so within conventional earth bag construction, one of the advantages it has over, adobe is the fact that the bag, which is, fabric, is very flexible. Right. And so in conventional earth bag construction, it can either be, like a brick geometry or block. It can be formed into like a keystone or an arch. It can be curved. So it's very malleable, it's kind of very malleable, almost similar to like concrete and such. And it can be a coil, so kind of coiling around, you might remember the 3D printing sort of technology. And so this is sort of a review of the potential, celebrating the sort of inherent flexibility of earth bag construction to kind of highlight the its suitability for like sort of different geometries. And so this is sort of addressed in previous research, the shrinking the sizes and experimenting with different geometries for earth bag structures. And this is a paper that I published in a TAD journal this past year. And sort of exploring how different geometries and different sizes of the earth bag can sort of influence the sort of aesthetic texture and the sort of the methodological construction process, assembly process of the wall, which translating into my current research is, it's not so much of a stretch to kind of imagine, okay, so even if like a pants or shirt doesn't follow the conventional traditional bag shape, it can be sort of modified to, kind of accommodate for that, or even sort of have different new potential uses of the wall. And so my question I'm kind of working on right now is, how can post-consumer textile waste be processed and sold to create durable earth bag components suitable for construction in a Center County, Pennsylvania context. So breaking this down, if we kind of remember the transfer of clothing between different places. So this left is essentially producers, the gray producing countries, and the gray are countries that produce and also receive waste. I don't know if this works. Oh, cool, awesome. So these countries, clothing is produced here, if we kind of lock in on textile consumption in the United States and further zooming in on Center County here, textiles are essentially sent to waste facility, thrift stores, or clothing banks, which kind of cycle back into Center County or are sent to landfill. Or they're sent to do Salvation Army to different countries. But notably, you know, if you look at the sort of transfer of all the textiles kind of going to these different places, right? If we look specifically at the recycling, the local model, the local textile recycling model in Center County, you can kind of see that in those in center here, they're either sent to clothing banks, thrift stores, or hobby reuse stores, which, you know, kind of focus on addressing and helping vulnerable populations here. The reason why this is particularly important is that when I spoke to the CCRA, the Center County Recycling Authority here, we don't have a municipal policy for recycling textiles, which is crazy. So a lot of the recycling of textiles happens at the local level. And I'm sort of wondering, how can I sort of insert earth-bearing construction into this sort of existing ecosystem of circularity? My research essentially is sort of situated in Center County with three different aspects. One, the soil that I use is from all the different development happening on campus, new buildings and such, so that's great. Of course, I use clothing waste that's taken from thrift stores here, and donated to me for my research. And there's also a potential, sort of human research or craft skill resource in terms of sewing craft expertise, in terms of like volunteers, student, hobbyists, and even local clothing guilds and hobby stores. So there's like a potential to kind of embed earth-bearing construction within Center County in a way that's very circular and like three different facets. So how can post-consumer textile waste be processed? So basically, as part of the research, I was sort of interested in the methodology. How exactly can I turn clothing into earth bags? And so my methodology is pretty much separated into two different phases. The qualitative, which essentially speaking to local clothing donation facilities and through interviews and getting that understanding of the sort of economy, and using designers research to iterate different earth bag geometries and construct wall prototypes. The quantitative phase, essentially, I'm constructing the wall now within Penn State to kind of measure their compressive strength and compare it to existing benchmarks. Interestingly, I actually presented an earlier part of this research a couple of years ago, so people might remember my presentation. Back then, I was sort of in this qualitative space, and now I'm currently in this space, which is exciting. And so when people who saw my old presentation, they'll be able to see like an update. And so how I essentially distinguish contract materials, I received donations of surplus materials from thrift stores saying, hey, do you have any spare clothes that I can use? And they're like, yeah, sure, take it. Because they're in surplus and that they're not selling them fast enough, which is also another problem because the material is essentially being bottlenecked in these donation centers. I essentially use image processing or binarization to measure the surface area of these fabrics. I'm using image enhancement to kind of identify the warps and the wefts, identify the type of seams or the types of weaves, and the sort of measuring the weight and density of these fabric materials to kind of understand categorize the different materials that I receive so I can use it for different parts of the wall. Seen this before, but essentially this next part of the process is essentially taking these garments and pretty much just like cutting them in half to make different shapes and geometries for the bag, to ultimately kind of use them in assembly for like a wall. And so these next series of slides will show, using closed earth bags. I'm wondering if they can be used to sort of replicate conventional earth bags. And so these are images from the conventional guidebook that a lot of DIYers use to follow it, and kind of using this as a process to kind of see if, these could be, methodologically like substitutes for polypropylene sandbags. And so, following along, kind of observing like so bag to bag interactions here and understanding, the potentials of, the more tubular bags using clothes, understanding, taking a look at, different ways of sealing the bags and twisting it to seal them closed or having them up against each other to kind of seal themselves. And also taking into consideration the vertical assembly of these stacks. So these are essentially, using recycled material to kind of bind these different components together as you kind of stack them up on the wall. And so the result was essentially what I called the pillow wall. I like to joke around that this is very deceptively called a pillow wall because they look like a bunch of pillows and they're soft, but they're actually quite hard because it's filled with compressed earth. And so what was kind of interesting about this initial prototype was that everything in this structure, except for barbed wire for tensile strength, is recycled and it's recyclable. So these are all cotton fabrics. So that's, biodegradable. This is elastic ties from your pants, so waistbands. So the elastic bands cannot be used for bags, but I kind of use it as support to tie down the barbed wire and each layer as they undulate through. There's like, this prototype is kind of interesting because it had a bunch of long sleeve shirts, so that kind of proves kind of interesting to kind of consider the different textures and the different ties and the business will happen when you stitch everything down. And there's like a lot of like overhang texturing due to the sort of a flexure of the fabric and also sort of all the different sleeves kind of poking out. So it's kind of neat and kind of fun to kind of consider the creative variability and the aesthetic variability of these different wall surfaces. And so just to speed ahead, because I think I'm behind, so using 3D scanning, I pretty much took that wall and kind of made it own 3D model to kind of also kind of iterate different improvements to this sort of wall design, taking into consideration with moving detail. And so my last part is, how can, this be used to create durable respective components? And so the earth that I use is taken from the physics building in Osman lab renovations, which is sort of in this area here. And it's urban land hagerstown complex soil. Essentially, all you need to know is that the texture of the soil is sandy clay loam. It's essentially when you work with it, it's very sticky, which is great for plaster, but it's not so great for compression because clay sort of swells and shrinks when it's like wetted and dried. But which basically means I just need to add like sand to it. And so understanding the sort of earth infill, filling up these bags, sort of resulted in a very laborious process of basically what I do in my research is I sift a ton of dirt and I sort of mix them all together with different combinations just to understand like what's the sturdiest, most durable mixture. And so there I mix between sand additives, which this process is this testing process is I make these bags, singular bags, I drop them from about 2 feet to see if they'll crack, just to see test the durability for that. And so with the sand additives, they kind of shatter, but with the addition of straw and a bit of moisture, you can see noticeably that the durability is better. So I literally have another sample that I just paid for this presentation, so I'm hoping that it's like a better combination. I hope to give you updates if that's successful or not. But this was really promising because, there's like a way to make the earth mixture more stable without using materials such as cement to sort of stabilize the soil. It's a more natural grown, more sustainable materials. And so right now I just have like a kit of earth bags that I made from all these different fabrics and these different components together to assemble a sort of improved version of the wall that I hope to do it semester. So I already designed and drew schematics for an updated wall that kind of takes into consideration different wall type structures in the conventional earth type wall in terms of like buttressing and door framing details. And also taking a look at different foundation components for, a conventional earth type wall. using these different modules to sort of stack everything together. And I conclude with, this is an updated version of the presentation I presented a couple years ago here. Before, I was looking at the different impacts of, materials and earth bag for using clothing for earth bags. The two most common materials are, polyester and cotton. And obviously, for my research, I'm focusing on cotton because it's more sustainable. But obviously, there's a question of like, okay, so what are you going to do with the rest of the material? So this is me sort of beginning to kind of grapple with, beginning to think about, what exactly other clothing materials that I can use for earth construction, sort of developing a catalog. As we can see, obviously, this is essentially a bunch of earth bag blocks left outside, exposed to the elements for over like a couple of years, with mud plaster and having them sort of wash away. Unsurprisingly, the cotton bags have already eroded, and the polyester bags are still, they're kind of a bit funky, but they're still sort of in shape there. And so I think this presents opportunity to kind of think about, okay, so maybe if I go back to this section, these different earth bags can be made from cotton, and other components can be used more resilient polyester to kind of deal with different parts of the ball. And there's also the opportunity to kind of use some of that material as sort of fibers to kind of embed inside the bag itself. So, in conclusion, I know I went through it quite quickly, but if you have any questions, I'm happy to answer.